This week, today, I'm going to post practice exams. I cannot do Wednesday night this week, but I can do Thursday night for a review session. So, I was just looking at rooms, and this room isn't available till 6:30. So right now, let's aim for 6:30 in this room. In the meantime, I'll try to find something else so we're not here all night. But if you don't hear back from me, that's what it'll be. 6:30, and we'll go over the example problems that I'm going to post sometime later this morning after my next class that I teach. Okay. Any questions about it? This Friday's exam is going to be work energy and impulse momentum. Okay. Those two, basically your last homework that you turned in, that big homework. This week you just have 2 problems for your homework because I want you to prep for the exam. Okay. Okay, so right now we're in the middle of rigid body discussions. Okay, right, rigid bodies mean that they do not deform. 2 points on the same body always remain the same distance apart from each other. That's going to be key in one of our the way we solve these problems is taking that into consideration. Later on, we'll talk about deformed bodies, like if you go into graduate school. Some other key concepts with this: if you're on the axis of rotation, you're not moving at all. Right, you're rotating. Right? Point A would be rotating around in a circle, but it's not moving. Right? It has a 0 velocity. Okay? And then any other point that's not on the axis will be tracing out a circle about that axis that is rotating. Right? Another key concept that we're going to use. If you look at that in 2D, right? If you're looking kind of down the axis, down this axis like that, this is what it would look like, right? You'd be tracing out a circle. That point would be tracing out a circle. As it went around point A, you can see that A doesn't move. Okay, we defined omega as being, right, we did this before with angular momentum. Omega is just d theta dt. It's the rate in which theta changes with time. And we're going to use vectors throughout this whole thing, right? You actually have to use vectors to do this right. So we're going to talk about our omegas being a vector. We rotate our fingers in the direction that it's rotating, and the direction that our thumb is pointed is the direction that omega is. It's a little weird to think about, but think about it, it's like the axis that omega is rotating about. That's the easiest way to think about it. The axis, so you rotate your fingers and go that way. If it's rotating the other way, right, then your thumb would be going into the board, and that'd be a negative omega. Okay, alpha, the same thing. The axis in which the omega is changing about, right, it can be determined with the right-hand rule. I always used to joke that these mechanics were harder for left-handers. We did talk about this. But really, with a left-hander, you can write while you're doing it, so we're at a disadvantage. The normal people are at an advantage. Any lefties in here? Oh, you got it right there. We got 1, 2 lefties. Yeah. You guys should make fun of them. Right, the rest of you make fun of those guys. Right? They're deformed. They're deformed a little bit. Anybody? Is this anybody's first winter? I always wonder. It just got here. Just got here from a. How about you done a winter before? I thought you said you're from a hot place in.
Yeah, it's pretty cold.
Yeah. Wait, just wait, man. Just wait. You notice how the sun's disappearing on us here? This is great. I love it. Right? As a sweater, I love this cold temperatures. Did you guys see the sun this morning? No. God, that's one thing that's nice about fires, right? The positive, really beautiful sunrises and sunsets. You gotta look at the positives. Okay. Right, so that's the key concepts here. All right, so note, to have the same 2 points of the same body will always have the same omega and the same alpha if they're on the same body, but they have different velocities. Okay, so we're gonna do a quick little review. This is circular kinematics from particles. Right, when we did in particular, this is normal tangent. Right? From normal tangent, I literally just grabbed these notes from the normal tangent section of particles. We define velocity as being r times omega in the et direction, right? So r times omega. Or you take the radius times the omega, and then they'll tell you the velocity. So if you look up here, right, if I was trying to determine the velocity of point B, I do that radius of the circle times that omega, and it'll tell me the velocity of B. And then it also comes out of it, too, that the radius of A is 0, and so it has 0 velocity. Okay? We're going to use that here in a second. And then eventually we're going to use this acceleration. So we're going to first talk about, velocities of rigid bodies. Then we're going to spend some time talking about accelerations in rigid bodies. Okay? We'll start out with velocities, go to accelerations. Right? So the first few notes are associated with that. And so accelerations are alpha in the ET direction. You have a component associated with that omega changing. And then you also have a component associated with the direction changing, which is the centripetal acceleration. We'll come back to that a little bit later. Okay, so now we're going to come up with our big equation that we're going to use here. Okay, so relative motion, we also did that in particles. Relative motion, we were saying that you can go from one point to another point just with vector addition. Right, call that RA. Oh, missed it. Call that RB. Right, and then there'll be a vector in between, and we'll call that RB as seen from A. B seen from A. Okay. All right, you can get to any point by going through another point. You go to there and then go to there. We get to find RB as that. So we could say RB B is equal to RA plus RB as seen from A. This is a quick derivation of the key equation that we're going to use. Okay. And get to RB, it's going to be the position of A plus the position of B as seen from A. So it's just doing this vector addition, just going to here and then going to there. Okay. Same thing would be true about velocities. Right? If that's how you get to positions, you could do the same thing with the velocity. Velocity of B is equal to the velocity of A plus the velocity of B as seen from A. Okay. And so one thing that we commented before is that, right, if I'm going to point B right here, B is going to be doing, if it's rotating about A, what shape is B going to be making? A circle, right? And in fact, it'll always just be making a circle, even if A is moving. But if we're relative to A, it will always be making a circle, right? And then we just wrote above the velocity in terms of omega, right? Because it's moving around in a circle. So let's just do that. We'll say VB, we'll say the velocity of point B is equal to the velocity of point A plus RB is seen from A times omega. Okay. R times omega is the velocity. And then, again, B is going to be making a circle about A. And so we just do that. Right, in vector notation, so I mean, that's just me to get you to buy in, right? You get that, right? This thing is rotating around. If I go to A, B is always going to be tracing a circle about A, and so I can just do RB is seen from A times omega, and that'll tell me that velocity, okay? In vector notation, it looks like this. This is the big equation that we're going to use. I'll highlight that with green. Okay. This is the equation that we're going to use. Right. If I want the velocity of point B, I just determine what the velocity of point A is, plus omega, the vector, crossed with RB is seen from A, right? Because B is going to be making a circle about A. And we write this, this is our equation. This is the thing we need to solve all of these problems, is this equation, right? So let's do an example to show you where we're headed here, or what we're talking about, okay? A simple example would be gears. This would be one of those ones, again, got out of a book, has a nice picture of gears, but instead I just drew two circles myself. I don't know why, right? All right, and so these are fixed axis of rotation. So both centers are fixed, so it's telling us that this point A here is fixed and point B over here is fixed, right? And so both of these are rotating. We're going to be given omega A and alpha A, and we're asked to find what alpha B and omega B are.
Shouldn't one of those be rotating the other way?
Well, yes, we're going to find that, yeah. But I'm gonna coach you to always draw them like this to begin with, right? And there's a reason for that. But you're absolutely right. One should end up rotating the opposite direction. Right, and this is the process we're going to use for every one of these things. Okay, what we do is we're going to start out at a point that we know something about, right? We're going to start out at a point that we know something about, and we're going to take a step to another point that we want to know something about, okay? Using this. This is all about stepping. We're going to step with this equation up here, right? So in this particular example, do I know the velocities of any of the points? Yes, I do. Yes, I do, Mark. Yes, I do. Right? A and B are zero. Those velocities are zero, right? Because they're fixed. They're not moving, right? So I'm going to take a step from A, and I'm going to go out to P, right? You can only take steps between 2 points on the same body. I can't go from A over to B because they're not in the same body, right? There's this gear, and then there's this gear, okay? So I know the velocity of A is zero. I know the velocity of B is zero. What's special about point P? Huh? It's on both bodies. It's on both bodies. It's on both bodies. What does that mean? What does that mean if they're both the same? In terms of velocities.
Oh, a little bit the same.
The same velocities. That's right. Look at you. A+ for you. You got B for Mark over here. You had one answer wrong, and then you came up with the right answer afterwards. Yeah, that's right. So, right? That's the velocity of point P is going to be the same, coming from both bodies, because they're attached to each other. There's no slip. Does it say no slip anywhere? This is why it would be nice to actually have the gears, and you'd see them, it's going in together, and so they can't slip between each other. So if there's no slip, then the velocities have to be the same. So we're going to use that advantage. What I'm going to do, how do I do it? How do I do it in my notes here? What I do in this one, as I said, I go from here to P, and I come up with an equation for the velocity of point P, and then I go from B to P, and then I set them equal to each other, right? That would work fine. I could also go from A to P, and then P to B, and then out would pop the relationship between the two. But there's enough information here to do this. Okay, so let's do what I just said, right? So let's go from A. From A to P. Right? So we say, what we do is just use that equation up above, right? There's the equation. I'm going to go velocity of P is equal to the velocity of A plus omega A crossed with R. P is seen from A. So I take that step, I just use that equation up above, but then obviously use the right variables in this case. I'm trying to take a step to P. It's going to be VA plus omega A crossed with R. P is seen from A. Okay. So then again, VA is zero, right? That's why we picked to start with that point. It has no velocity today. And so then we just expand this thing out. VP is equal to omega A in the K direction, right? The way it's drawn, we're given omega A. Rotate my fingers in the direction A. It's coming out of the board. So that's omega A in the K direction. And I'm going to cross that with our P is seen from G, right? So that radius here is RA. And so it's important that you go the right direction. Our P is seen from A is going that way. Right? I'm going to P from A, right? So that is going to be RA in the I direction. Right? These are vector equations, so everything has to have a direction. All right, now we got a cross product. Anybody remember how to do cross products? I don't like them, right? And so I'll give you. We're gonna do it in a short. And when we do examples in class, we'll do it. A trick. We'll do a trick because there is a way that like you set up like a row of zeros, and then you do like the determinant of it or something like that, right? There's some way of doing it. Then there's a little IJK thing that happens. Or what I'm gonna do is how I do it is I take my fingers and you point in the direction of the first thing, right? So I got the K. So K, omega's in the K direction. So my K is coming out like this, and then I rotate my fingers in the direction of the thing you're crossing it with. So I rotate it in the I direction. And then the direction your thumb is pointed is the direction that cross product is going to take place. So that would be RA omega A in the J, right? K, I, thumbs pointed up. So it would be in the J direction. So this velocity of P, right? And then this, we'll look at it here in a second. RA omega A in the J direction. Right? And then you might be like, well, that's obviously, right? So what that just said was P is moving this way, because that's what we're finding, right? We're finding the velocity of P. And P, according to this, when we just did this cross product thing, it says P is going up with R omega. Right? Duh. Right? Duh. Right? I mean, R omega is our velocities. Clearly, if it's rotating like this, it's going that way. So you're like, oh, I don't need to use this cross product thing. Things get out of hand really quick. This is the simplest thing we could do. So I would always recommend just doing this method. Using this is taking a step from one point to another point and going that way. If you start just later on, we're going to have some things where the velocity of A, this point right here isn't fixed. And so it isn't clear like what direction things are going to be moving, because A is moving a certain way and then you don't know if it's going up or if it's going down, but this math will help you, okay? So that's one way. That's how I do it. I think it's the easiest way, like in class, to do this. The other way you could do it, I think there's this, you may remember this from math. There's like a little thing, J, and a K, and then little arrows in between them. That's something like that. I think that's right. All right, so if you go, so K crossed with I gives us a positive J, but then if I did a K crossed with J, it would give me a negative I because I'm going the opposite direction. And so there's a little trick with that. I don't know what it is. Okay. The other thing you could do is set this thing up as a row vector or a column vector. Right? You could do, right, this particular one would be, it would be a vector. You can this 0, 0, omega A, and then crossed with RA 0, 0, and then that. If you do it, the only reason I'm showing you this is because your calculator will do this. RA omega A 0. This is how you would do it with your calculator. And honestly, I don't know, I've been messing around using my calculator with these vectors. It's pretty nice, right? Sometimes it takes a little bit of time to enter it in, but literally in your TI-89 or Inspire, I don't know about your 84s, is, you put the square braces, you do 0, 0, I always just use like X because that's what I know, crossed with Y, 0, 0. And then there's a command, like if you hit catalog, and then hit C, it'll take you down to cross product. You can do cross product of that guy, and then out would pop this guy, right? So sometimes when we get these, like this rack and pinion gear, when you have all sorts of stuff going along, sometimes using your calculator might be nice, right? I'm fine with it. Use your calculator. But also, make sure when you're doing it, you're documenting all these steps as you go along. Some of these later ones, use MATLAB. Right? MATLAB is really good with vectors and stuff like that. It's actually beautiful to do that. Okay? So that's our first look. I'm just going to do for class, I'm going to do the right-hand rule stuff for calculating these things. Okay? Any questions about this stuff? Okay. You've done it before, just maybe not applied it. All right, so then we're going to go from B to P. Right? You can do whatever you want. You step around however you want to step around. Right? Like I said, I'm going to do this one where I'm going to go A to P, P to B, and I'm going to set those velocities at P equal to each other, and out will pop the ratio. But you could go A to P and then P to B, and then just enforce that B is velocity of 0, and then out will pop the same answer. Either one. So from B to P. Right? So we're going to do the same thing. So VP is equal to VB plus omega B crossed with R P is seen from B. All right. So this goes, now we're to your question earlier about which direction is omega and which direction is alpha, right? That's a great question, right? So at this point right here, right, say I didn't show this. Say I didn't show that at all. And that'd be valid. I could say that. I could just not show you that. I showed you that just so that you knew where we're going for. But really, a type of problem like this, I wouldn't tell you I wouldn't show you a direction. It would be up to you. What I recommend always doing is assuming, like, it's an unknown. It's an unknown at this point, right? I don't know which direction. I do know because I'm no dummy, right? I do know. But in some of these complex problems, you don't know which direction it's moving. And so what I always say, just assume it's positive. And then you'll just make it positive when it goes into this equation down here. And then when you solve it, it'll turn out negative, which means that it's not positive, it's negative, right? Which is beautiful. It's a nice systematic way of doing it. I could, I don't know it, I could come out and say, well, I know that thing is gonna be negative. I know it's going to be negative. I know it's going to move that way, which I do. I know if this thing rotates like this, it's going to push that turn. It's going to make this thing rotate this way. I do know that. So I could draw it up here and say, yep, it's going to go that way, right? And if I draw it going that way, and if it turns out positive, it means that it's negative. If it turns out negative, it meant that it was positive, right? So, do you see what I'm saying? Like, it gets a little confusing. So just always say it's positive going in. It'll turn out negative. Then it turns out negative, which means it's negative, right? Huh? Okay. Yeah. It's a no dummy. Maybe I am. Maybe I can't handle that. I can't handle negative being a positive being negative. Okay. All right. So velocity of B, again, that's going to be 0, right? And so if we expand this out, VP is equal to omega B, again, assuming it's positive, and I cross it. Now, though, again, I'm going to P from B. So that's that vector right there. P from B, so that's going to be negative RB in the I direction. Negative RB in the I direction. Okay. So then we'll do the right-hand rule again here, right? Fingers come out in the positive K direction. Then I cross it with a negative I. So I curl my fingers in the direction of negative I. Negative J. Fingers going down. Negative RB. So it's just multiplication and then the direction it's going based off the right-hand rule. Okay? So then at this point, we're ready to set them equal to each other. Vector VP is equal to vector VP. R A omega A in the I, or in the J rather. Ooh, yeah, that's a J, yep, in the J is equal to negative R B omega B in the J direction, right? Good thing they're both in the J direction, otherwise we'd be in trouble. So there's a relationship. Omega B is equal to negative RA over RB times omega A. Right, there's your negative. There's your negative they're looking for. There, one's going to be going one direction, the other one will be going the opposite direction. Right? This is gear ratios, right? These are how gear ratios work. Right? You can imagine like a bicycle wheel, right? These things aren't actually touching, but they're over here and they're attached with a chain, and there's no slip between chains, and that's how we get those different gear ratios and stuff, or in a transmission or something like that. Right? But again, this gear ratio thing, I get it every time. This gear ratio thing only works when you have two fixed points. What if A was moving, which it can be, right? It could be rotating around B as it was rotating, right? So you just gotta be really careful. Don't just jump into this. This only works when you have like two fixed things, okay? Any questions about this? This is how we handle these problems. Same steps every time, right? Taking a step from one point that we know something about, taking a step that we want to know something about using this velocity equation. The second part was what is alpha? We just take the derivative of this. We're going to get into accelerations later, but you just take the derivative of this, which would just be negative RB, or RA over RB times alpha A. We just took the derivative. The only thing changing with respect to time in that is omega. We're gonna do accelerations a little bit later. Okay. Okay. All right. Let's talk about rolling wheel kinematics. This is we use a lot in our solutions. Right, we'll have something that's that's a wheel and it's rolling and it's attached to something else. And so this is kind of important. This is another good example of taking steps around here, okay? And so we're just gonna do velocity first. In a couple of days we'll do accelerations, right? So in this case, what they're giving us is the angular velocity, omega. They've given us omega. That's a given, right? There's no slip. And then it's asking for the velocity of B and the velocity of A, okay? This one always blows my mind, and actually didn't even think about until I started teaching this class, and I was like, oh wait, that's really weird. Do we know the velocities of any point on this body? A rolling wheel. Yeah, what's the velocity at C? Isn't that weird? And not, obviously not to you. It was weird to me. The velocity of point C is 0. I was like, wait a minute. Like if I'm driving in a car and I'm flying down the highway at 80 miles an hour, when my tire touches the ground, it has a 0 velocity. It has to have a 0 velocity, right? A 0 velocity relative to the ground, right? So it's coming around. Because if it didn't have a 0 velocity, you'd be spinning out, right? You'd be spinning out. There'd be slip that would be happening here. But otherwise, it can't be moving, right? At that point, it can't be moving. I don't know. Is that just me, or is that weird? I never really thought of that, right? The velocity at the tire is 0. Velocity at A, absolutely not 0, right? It's going to be traveling that direction. One way that helped me visualize this was if you trace the path of point C. If you trace the path of point C, it's doing this, right? It's coming in like this, right? And then it's going. And then I'm just like, oh yeah, okay, I see that, right? Because that's where C's coming in, right? It's coming in, it's like going, touching, and then going up like this, right? Touching, going up like that, right? That helped me. It's like, okay, yeah, I buy that then, right? So we do know the velocity of a certain point, right? So I know the velocity of point C is 0. So let's do VA first, right? Right? And again, it's really nice. You start at a point that you know something about. I know the velocity of point C is 0, right? So you go. So VA, velocity of A is equal to the velocity of C plus the velocity, plus omega, only one omega, crossed with RA is seen from C. Right? And again, I know that velocity C is 0. Right? Because just the rolling wheel kinematics, right? You won't be able to solve some of these problems if you don't recognize that. Right? You know that recognize where it's touching the ground that has a 0 velocity. Even if it was on the wall on the side, where it was touching that wall would be 0. Right. All right, that omega is omega in the k direction, so you just expand that, put it in its vector notation. VA is equal to omega in the k direction, the way it's drawn. And I cross it with RA as seen from C, which is R in the j direction. Right, that radius is R, and so it's this way. Right? You always have to make sure you do that in the right direction. That's R in the j direction. So now we got a k crossed, k coming out, crossed with a j, gives me a negative I. Is that right? K crossed with a j gives me negative I. So this would be equal to R omega in the I direction, a negative. That is the velocity of A. After doing, like I said, I'd highly recommend using this vector. The way I do is I do vectors, and then afterwards I come back and say, well, does that pass the stink test? Right? Does that make sense? Okay, I got this thing, say velocity of A is gonna be R times omega in the negative I direction. Yep, and I'd buy that, right? If this thing's rotating like that, it's gonna be an R omega in the I direction. It's gonna be going that way. Same thing with up here, right? We talked about before, velocity of P, we said it was going up, and then if omega was positive, VP would be going down. And that's what we got, right? We got VP going down. So I always just look at it after and say, does that make sense? Right? And so there it is. That's the velocity of point A, right? Now at this point, I was asked for the velocity of B. I could do a couple different things, right? I could go to B, and we'll do both of them. I could go to B from A. I could go there, right? Because I now know the velocity of A, right? If I know the velocity of A, I can go out to B. Or I could go from C to B as well. Either one works, and I should get the same answer. So we're gonna do it both ways just to show, right? 2B from, we'll go from C first. 2B from C. I say VB is equal to BC plus omega crossed with RB is seen from C. BC is 0. Right. So this is equal to omega in the K direction crossed with RB is seen from C. RB is seen from C is this guy. Right? And so that's going to be over R and up R. Both of those. So that'll be crossed with R in the I plus R in the J. Okay. Put in both the I's and the J's. So we got omega in the K crossed with positive I gives me a J direction. So it'd be R omega in the J. R omega in the J. I'm putting over on the right there because I know an I is coming up. I got a K crossed with a positive J. Gives me a negative I. So then I get a negative R omega in the I direction. That's VB. Okay. You don't have to do I's first and J's second. Yeah.
Where did you get the RI plus RJ from?
Oh, yep. So it's this vector right here. It is this vector. I'm going to draw in green. Right. It's that vector, right? So it's got to go over radius R in the I, but then up R in the J.
That makes sense.
Yeah.
Okay.
Yep. All right. You don't have to do I's and then J's afterwards. I just like to do that, and I knew it was coming up, so I left a little space, right? But it makes it a little bit easier if you do. I just do I, J's, and then K's, right? And this would be one where the calculator might be all right, right? Because you got set that sucker up and you have, 0, 0, omega, and then you cross it with R, comma, 0, and then it would pop out that you would get this, right? You could either one. Okay, so that's to be from C, right? You don't have to do both of them, right? To be from A. So I'm pointing out you don't have to do both of them. Sometimes I do this where I kind of do it two different ways to show you get the same answer, and then people do that on an exam. They come from all different places. Don't do that, right? This is just an example. To be from A, right? So then we do here VA or VB. VB is equal to VA plus omega crossed with RB is seen from A. Right? Now VA isn't 0. VA is what we found above. it's this negative r omega in the I. Ooh, I'm going to go back. VB is equal to negative r omega, capital R is what we're calling that, negative r omega in the I direction plus omega in the K crossed with r in the I. Okay. VA, what we found out, it's up here. Right. So you just put in that, because that's now a known, right? And then we do omega in the K crossed with r in the I is going to be the vector, just r in the I direction. And so that's going to give us a K crossed with a I gives us a positive J. So same answer. VB is equal to negative r omega in the I plus r omega in the J. Sick. Right? Again, back to the sting test. Does that make sense? If this thing has rolling with an omega, VA, we go in the I direction, right? In the negative I direction, right? If it's rolling like this, A should be going that direction, right? Which it is. And then point B, it's also moving in the same velocity as point A in the I direction, right? Negative r omega in the I direction. But then also it's moving up, right? Which passes the sting test. So absolutely, you should be doing both of those things, right? It should be headed that way, right? It's going this way. It's on its journey that direction, right? Cool, cool, cool. Cool, cool, cool. All right, let's do a real deal. These are just the very basics here. Let's do this guy. All right, you look at this, you're like, oh my God, look at all this. What do I do? What do I do? Right? Son of a bitch, right? Just stick to the plan. Our plan is we start at a point we know something about, and then just start working our way around, right? And then we'll get hung up someplace, and there'll be some too many unknowns, but just keep going, keep chugging, right? So, a couple key concepts here. Point A is fixed. And then also point D is fixed. That's why I kind of drew this extra little thing coming down just to show it's fixed to the ground. So point D is not moving, point A is not moving. Again, you kind of see what's going to happen, right? Like we're given this 10 radians. So this thing's going to rotate down. It's probably going to move this point down, which is going to kind of move that, and it's probably going to push this point up, which is then going to move, this guy down, right? And again, your intuition may throw you off here, right? Because there's a lot going on. You got, maybe it's going to rotate one of the other directions, or maybe it'll rotate the direction we think. Don't worry about it, right? Just stick to the plan and work our way around, right? So what's given to us is over here. They give us this omega being 10 radians per second over here, and I know velocity A is 0. So I'm going to take a step from A to B, then I'm going to go B to C, then I'm going to go C to D. And then once I do that, then I'm going to go D over to here. Right? So you just work our way around like that, right? And they look intimidating to begin with, especially if you're going to do this one in your homework next week. It's a sun gear. Okay, so there's like a gear in the middle, and then it's got all these gears around the outside, and then a gear like this, and then some more gears over, right? It looks really intimidating, but you just stick to the plan. And then also be thankful, civils, that you're not mechanicals. You don't have to do sprockets when you grow up. Yeah, when you grow up, right? You just have to do them now. You don't get to do weapons, but you also don't have to do sprockets. Yeah, there's lots of weapons. Lots of weapon design. Okay, so let's do that. Let's go to B from, start working around. To B from A. VB is equal to VA plus omega AB crossed with RB as seen from A. Okay, velocity A is 0. Right, and we can start subbing in values. They actually give us what omega AB is, right? And this time you do have to be careful about the signs, right? They give us omega AB, right? Rotate your fingers in the direction of omega AB, right? Thumb is pointed in, so that's a negative K direction, right? It's rotating like that, so it's a negative K. So it's a negative 10 in the K direction. So VB is equal to negative 10 in the K, and I'm going to cross that with, right, I'm going to B from A, so it's this vector here, which is going 6 in the I and 12 in the J. This would be 6 in the I plus 12 in the J. Right. Do the cross products here. I got my negative K. Oh, I don't like the negative K's. Negative K. I'm going to cross that with a positive I. Right? It'll be a negative J. Negative 60 in the J. VB is equal to negative 60 in the J. And then I got a negative K, and I cross it with a positive J, positive I. And so that'll be plus 120 in the I, right? I'm just showing that you don't have to do I's first and J's later. Sometimes it's just a little easier to do that. That's the velocity of B. Right? Again, I like to look just as pass the Sieg test. Are those directions right? Negative 60 in the J. So if this thing's rotating like that, it says that guy's going down and it's going that way. I'd buy that, right? So I did my cross product right? B should be going down and should be going to the right, which it does. Okay, keep going. Now we're going to go to point C. And things are going to bog down here a little bit. VC is equal to VB plus omega BC crossed with RC is seen from B. Right. At this point right here, right, I'm pretty sure BC is going to be a positive when it comes out. It's going to move down. I'm pretty sure it is going to be a positive, but it doesn't matter. I'm just going to assume, no matter what, if it's an unknown, I'm going to assume that omega is doing this. Okay? Even if it's not, I'm just going to say that it's always going in there as positive. Okay? But I don't know. It's an unknown. I don't know which direction it's going. Right? So then we just keep going with this. This is going to be substitute in VC is equal to 120 in the I minus 60 in the J. That's VB plus omega BC in the K crossed with RC is seen from B. RC is seen from B. I'm going this way and I'm going this way. So I'm going over 16 and down 2. Crossed with 16 in the I minus 2 in the J. This would be where, like, if you had this sucker in your calculator, I could see this being not so bad because you'd have your vector that, and then you'd have the omega 00K, and then you'd have the 16 and the negative 2, and you just add them all together, and it would just take care of the math for you, right? I'd play around with it. I'd mess around with it. I'd do some of your homeworks with it like that. Because you have your calculator with you on the exams, right? So right, you can carry out this cross product. This would be 16 omega BC in the J plus 2 omega BC in the I. That's what that guy is. And then you lump your I's and your J's. VC will be equal to 120 plus 2 omega BC in the I plus negative 60 plus 16 omega BC in the J. You notice it's bogging down on us a little bit. Because I don't know what omega BC is, right? Right, so you just lumped it. I can see a calculator being helpful for this. Right, or MATLAB. Right, I got my I's and my J's. Right, but I don't know what omega BC is. Right? I don't know what omega BC is. So I'm not, right, so you're kind of bogged. I can't put actual numbers in there, right? Because I can't solve it yet. So what I got to do is I got to keep going, right? There's a couple ways I could do this. I could say, well, I now know the velocity of C, right? I know the velocity of point C coming from B, right? But I could also go from D to C, right? And then they have to have the same velocity, right? Because they're attached to each other at that point, okay? So that's how we did the sprocket one, right? We went from here to here. Actually, in this case, we're going here, 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 here. And then I could go from here right to here and set those equal to each other. Could do it that way. Or I could keep going. What I'm going to do is I'm going to go here, here, and then to here, right? And which you could do. And I just know that the velocity of D is going to be equal to 0. So let's do it that way, okay? So now you just keep chugging along. They're kind of tedious. These are tedious and lots of bookkeeping to do, but the method isn't that bad. Right? VD is equal to VC plus omega CD crossed with RD as seen from C. All right? So I'll just plug in what we know. VC is this big guy up here. What's this? Cheat because I can. Get rid of that blue. That's VC. Oh, I didn't give myself nearly enough room. Plus, again, always just assume that omega CD, or that your unknown is going to be positive, right? So omega CD in the K direction, and I cross it with RD as seen from C. That's this vector right here, right? So it's going down 10 and to the right 6. So I go 6 in the I minus 10 in the J. You carry out that cross product, let's give you the answer there. 6 omega CD in the J plus 10 omega CD in the I. Make sure you could do these cross products any way you do it. I'm not going to spend any more time doing the right-hand rule on the, but you do the right-hand rule or you do it with your calculator. That's that. And then again, you lump all your I's and all your J's, right? But then what do I know about VD? It's equal to 0. So in this case, I know this side. 0 in the I plus 0 in the J. Okay? I know that. That's where I know that those velocities over there are 0. So now lump all your I's, lump all your J's. Okay, so let's do that. 0 in the I plus 0 in the J is equal to 120 plus 2 omega BC plus 10 omega CD, all of that in the I direction, plus negative 60 plus 16 omega BC plus 6 omega CD, all of that in the J direction. Myself in a room. See how tedious these things get? But a lot of bookkeeping, but you just lump all your I's, all your J's. So then this guy has to be equal to 0, right? This whole thing has to be equal to 0, and this whole thing has to be equal to 0, right? On both sides of those things, right? And then what are our unknowns? Omega BC and omega CD. I know, in both of these, so those are 2 equations and 2 unknowns, right? You look in your I, you look in your J, right? This is equal to 0, this is equal to 0. Where are we at in time? Oh, we got 1 minute. Let's finish this sucker out. Right? I'm gonna say that. Looking I, looking J. Uh-oh. That's what this last step is. So I literally put that in my calculator. 120 minus 2 or plus 2 omega or 2x plus 6 or plus 10 y is equal to 0. That's one equation. The other one, negative 60 plus 160 x plus 60 y is equal to 0. Solve for x and y. And then what you get is omega BC is equal to 8.92 rads per second, and omega CD is equal to negative 13.78 rads per second, right? And we made the assumption above, right? We made the assumption that BC or DC was going to be a positive, right? In there, we said it was a positive. We said it was in the positive K direction. But now omega CD turns out to be negative, so it actually is going that way, right? Which our intuition would say, right? Going down, twist it like that, making that thing rotate in the negative direction, right? Rotating like that, right? And at this point, now I know the omega of the whole gear here. I know of all the gold, and so I go from D to R. The last step was R. We'll just finish that off so we don't have to do it next time. VR is equal to VD plus omega CD crossed with R. R is seen from D. Right? VD was 0. That's a fixed point. The VR is equal to negative 13.78 in the K direction, crossed with 6 in the I. And what you get there is negative 82.68 in the J. Inches per second is what the units on that are. It's called a rack and pinion gear is what this thing's called. Right? Rotate it, push it, goes down. Right? The other thing, just before I let you go, a couple things to note here. When you solve these problems, you solve these at the instant that it's shown. Within milliseconds, all of that geometry changes. Right? You see how that happens, right? All the 6s and the 10s and the 2s and stuff, that geometry, immediately after movement, it's changed. That's beyond the scope of this, right? But really, in the real world, you would have to trace what those are doing as a function of time, right? Because all those dimensions would be changing. That's beyond the scope of this. We're going to solve these problems at the instant they're shown, right? And then also, does that pass the sync test? I think, right, going, and that thing would go down, right? And so that's the relationship. Somebody else was going to tell you about this, but just be careful. Just be really tedious with these things. Right, this is kind of as complicated as they get. We're going to do accelerations next. We'll do one more example in accelerations next if things get out of hand. All right.